Hi everyone, my name is Roman. I work at a company called Sentry, and today I want to make a deep dive into how we build a new product, which is called Session Replay. Before we begin the deep dive, I just want to give a quick introduction to Sentry for those of you who don't know. What is Sentry is application monitoring in production, so we monitor errors, performance, we do profiling, many other things. It's a developer tool built by devs for devs, so we ourselves are devs. We have some apps in store, and we dog food our SDKs, our Sentry product with our apps. It's open source completely, so you can go check out the main product source code. Our SDKs is also open source, so you can go see it on GitHub. And it's free in a way that you can actually self-host this on your own infrastructure. And we have a generous free tier to start with if you're a small team or a small app. We support over 100 different SDKs and languages: Android, iOS, Flutter, React Native, Kotlin multi-platform, even Xamarin if you are adventurous. Yeah, so these are like the core features. I just highlight them quickly. So we have crash reporting, where we attach some different metadata, like screenshots or text in this case. We do have performance monitoring, where you can see the timings of your app, like app start times, HTTP requests, and so on. And as I mentioned, we also have profiling, where you can see like how slow your functions are or how fast they are. But today I'm going to talk about the new cool thing, which is Session Replay. And let's start with what we are going to build. I recorded like a short showcase video where you can see the steps you can perform within the product. So you can start the replay and it plays like a video. On the right side, you have like breadcrumbs that showcasing like, these are basically bookmarks in your replay. You can navigate through them. Then you have network requests. You can see like their timings, at what point in time they happened, and what was the response or request body, for example. You can then, of course, navigate forward in the replay timeline or back, and you can click on some certain breadcrumbs to speed up the playback. And yeah, next we have the errors tab, where we kind of capture all associated errors with this replay. So what errors happened during this replay, in this case, like this illegal state exception. We also have a trace where you can see like your performance metrics along the replay, how it's going. And finally, we have text, which you can filter by when you're looking for different replays. And in this case, we are filtering out like for this specific release. So to list some requirements, we're building like a video-like reproduction of user activity. It has to be connected to errors, traces, or other areas of our product. It has to be high fidelity, so you can actually see what's happening on screen. It has to be low performance overhead, because we don't want to downgrade the performance of your app or even crash it in any case. And lastly, but most importantly, we have to have a possibility to strip sensitive data. So for example, if you're building a banking app, you don't leak like, I don't know, user amount of money on a bank account or some different other things like passwords or username. I just quickly showcased how it would look like. So we have like a screenshot on the left side, and after that we apply what we call masking process, and then it would redact everything which we think is sensitive. So in this case, text, views, labels, and all the media. When we decided to build it, we kind of looked at the open source solutions, if there is any. Unfortunately, there are not. But there are already some existing products that are doing that. So we went ahead and investigated what are they doing actually, what are the possible approaches we could take. And the first one was to take a raw video recording and then replay. I think iOS and Android, they both provide a means to kind of record screen. The second approach would be to capture the view tree and then transform this into HTML elements so they can be replayed on the front-end part, on the front-end side. The third approach would be to capture the canvas draw commands and then reproduce them on the web HTML5 canvas. Because those commands are very similar between platforms, you could actually redraw your UI on the web page but it would look like it's a mobile app. And the last approach would be to periodically capture screenshots and then stitch them together into a video. So we investigated the overhead, so put up like a short, small table with some numbers. You can see them here. You can see, for example, that the raw video recording is quite heavy on CPU and memory. And the best performing approach is actually canvas draw commands. But we went with the latter one because it has the best fidelity, and it's actually not the most resource-consuming approach. So it was a good trade-off for us. With that knowledge, let's build some replay. So we identified some key pieces for us which we want to have in our product. And the first one would be what we call replay video. And it basically contains actual video bytes that we created from screenshots. The second piece would be what we call replay recording. This contains all the metadata that you've seen on the example video on the right side. So there will be breadcrumbs, user gestures, logs, network requests, and so on. And the third part is the replay event, what we call, and it contains some Sentry-specific data, for example, tags or connects to errors. And yeah, after that, we would package this all together and send to our backend for processing. But in today's talk, I want to focus on the first piece because this is like the most interesting part of this product. So we're gonna make a deep dive here. Let's go quickly through the algorithm for the replay video. So we have to choose some certain frame rate. How many screenshots per second do we take? By default, we chose 1 FPS because I think it's a good trade-off between speed and like fidelity of the replay. Then you have to take a screenshot of the entire screen at that frame rate. After that, you have to capture the view hierarchy of the same frame, so that the screenshot and the view tree are not going out of sync, so you can mask properly the sensitive data. Then you would apply masking with all that knowledge. Then we would store screenshots to disk, so in case our app crashes or there is an ANR happening, we would not lose those frames, and you could reproduce them when you're experiencing an exception. Then you want to rewatch what happened prior to that. And the final step, we want to create a video segment from those stored screenshots. We chose 5 seconds video segment here to kind of have small chunks of videos that we want to send from the SDK to not consume a lot of network bandwidth of the device. Yeah, let's go ahead and implement the first part of it, and this is taking a screenshot. So as I mentioned, we want to have some kind of recorder config that we expose to our customers or developers, and the default frame rate would be 1. Then we would create a separate thread, we call it Sentry Recorder, and we would just launch this thread to repeatedly call capture at the certain frame rate. So we just divide the 1,000 milliseconds by the frame rate here. So if you would specify, like, I want to have 2 frames per second, then we would capture a screenshot every 500 milliseconds. Yeah, let's then implement the capture method. So for years, there have been a way to capture a screenshot, and the way would be to get the root view of your tree and then call draw on the bitmap. But this is very inefficient because it would have to redraw the entire view tree again on the bitmap, and you kind of already have this on the screen. And that's why, I guess, Google came up with this new API, which is called Pixel Copy, which has this method called request. And what it does is it actually gets the most recently queued buffer in the window, and it will basically copy those pixels onto the bitmap. So you would not need to traverse the root view and redraw it again. You would just take those pixels and just copy them on the bitmap, which is super efficient. The only problem was that it got introduced only in API level 26, but it was fine for us because we would still cover like 95% of the devices, and it was a good trade-off. So we just get back to our method. We add the requires API annotation. Then we actually have to switch back to the main thread at this point because capture, as you remember, is performed on the background thread. So that's why we use here the main handler. And we just call pixel copy request. It has 4 parameters: the current window, the bitmap, so it's the resulting screenshot. The listener is the callback, which will be invoked when the screenshot is done, is captured. And the listener thread is where this callback will be executed. We still chose the main thread here, but we'll get back to this later and explain why. So we have a couple of parameters with to do. The first one is window, and how can we get the current window? There is a nice library from Surprise Square, which is called curtains, and it kind of simplifies working with window management on Android. So it wraps a lot of things in a nice API. So we just go ahead and use it. We call curtains and add this on root view change listener, and this listener will be called whenever there is a new window added to the app or whenever it's removed. And we just keep track of those windows in an array list. After that, we go back to our capture method, and we get the most recently added window, so the one that is basically current screen, do some sanity checks that it's still visible, and use the window as a parameter for pixel copy. The next parameter would be the bitmap, and we just create it, pretty simple, but we still have to fill in the width and height. And for that, we'd have to use the width and height of the device screen, so the device metrics, screen metrics. For that, there are 2 APIs actually. So one is the get real size. Unfortunately, it was deprecated, but it basically gets the size of the screen with system windows also. If you have like a bottom bar, it would also include it. I forgot to mention that pixel copy actually takes the screenshot with the system bar, so we have to consider the real size here. As I mentioned, this method was deprecated, and the replacement is this get current window metrics. So we just go ahead and use both, depending on the API version. So we just retrieve the window manager and then use one or another, depending on the API version. And then we use the screen bounds as width and height for our bitmap. Now we can already go further and implement our callback. We still have to check for the copy result, so it has to be successful, which means the pixels were copied over to our bitmap. In case it was not successful, we still have to recycle the bitmap to not consume unnecessary resources, and we just return early. Otherwise, we fall through, and hooray, we have a screenshot now. And at this point, it would look like this. But as you remember, our end goal was to have this basically a screenshot masked, which brings us to the next chapter, masking screenshots. If we look at the screenshots, there are multiple view elements that we can identify. So for example, we have an image view, we have a text view, we have a button, which is essentially a text view because it actually inherits from text view. Then we have like a navigation icon, which is essentially, again, an image view because it inherits from image view. And same with the navigation text view. Of course, there can be other views like web view or maps that you have to mask, probably. But masking only image views and text views would probably cover you with like 95% of the cases. So that's what we've done. Let's go shortly through the masking algorithm. So we have to walk the view tree from its root, check if it's a text view or image view, check if it's visible, and retrieve its bounds, and retrieve other necessary information for masking. Otherwise, we just skip the view and don't mask it. So I just created this simple seal class called view hierarchy node, and we only have necessary parts of the views that we want to capture, like should mask and the bounds of the view, and like different types, text and image views. Then we created like this helper method from view, which receives the view, and then depending on the view type, whether it's text view or image view, it kind of maps it to our internal structure. We still have one to do here, which is like how to retrieve the bounds of the view. There is a method for that, which is called getGlobalVisibleRect. And what's interesting, it also actually checks whether the view is currently visible on screen or not. And it will set the coordinates of the view to that rectangle that you passed there as a parameter. So we just go ahead and do that. We create our empty rectangle and then call this method. Yeah, now we actually know whether the view is visible or not, and we have the bounds of the view. So we just pass them to our internal data structures. The other part that I didn't touch yet is basically the view tree traversal, but this is some basic stuff, so I'm not going to walk you through it. But the outcome is basically we'll have a list of rectangles that we want to draw over our screenshot. Yeah, so we just go ahead and use this method. And at this point, we can actually switch back from the main thread already because we already captured everything we needed from the main thread, the screenshot and the view hierarchy, and we can already submit it to another thread. And remember that our internal view hierarchy structure doesn't contain any Android-specific things like context, so we are not going to leak anything. Yeah, and let's just draw our rectangles over bitmap. So we create a canvas of this bitmap, we create a simple paint with black color, and we iterate over our list of rectangles. When you execute that code, it would yield something like this, basically, the screenshot with black areas. But as you remember, it's still not the result that we wanted, right? So that's the result that we wanted. And what's wrong here is that it has the wrong color, and the text layout is not considered here. So we see that there is like a single rectangle instead of like 3 for the multi-line text. So it's not really reflecting the actual representation of the screenshot. How can we get the text layout? It's pretty simple because Android Text 2 exposes this layout. So we can just go ahead and use it, and this layout contains all the info that is necessary to kind of draw text on screen, like the text color, how many lines it has, the line start, line end, and so other different things which are useful for us in this case. So we just add this new property to our text view hierarchy node, and we just retrieve it through view.layout. Then I created this simple extension function that returns us a list of rectangles for the layout. And as I mentioned, it exposes this line count, so how many lines this text has, and other different methods. For example, in this case, we can get the line start and line visible end. Then if we go further, we can get the line top and line bottom. I try to visualize this on the side, what those represent. Next thing is those line start and line bottom, they are actually relative to view coordinates, which means in this case, line start would return 0 for us, but we actually want to map it back to the global views, right? So we still have to consider the global rectangle here. And yeah, like that, we can actually retrieve or calculate the rectangle for the first line. Then rinse and repeat, do this for all other lines. And yeah, then we can go ahead, go back actually, and use those rectangles. So we just retrieve them and then iterate over them and then draw for the text view. After running this code, you would have something like this, which is already looking nicer, right? Because you have rectangles per line, and it's easier to perceive this screenshot, I would say. The next thing we want to do is get the dominant color. Yeah, so getting the dominant color of the text is pretty easy because layout exposes the text paint, and this paint contains the color with which was used to draw the text on screen. So we just use that one for our drawRect method. Pretty simple. However, for images, there is no such method. So you cannot just get like, what is my color, dominant color of the image? So what we came up with, we kind of wanted to get our image, then create a single pixel bitmap, and basically scale down this image to the single pixel bitmap. After that, we can reliably, I mean, almost reliably, get the dominant color because it would like be prevailing over other colors after downscaling. So let's just go ahead and do that. We create a single pixel bitmap, create a canvas for it. Next question would be how can we actually draw this part of the screenshot into this bitmap? There is this nice method on Canvas, which, I mean, I think I'm not going to read it, but basically what it does is it gets your screenshot and gets the part of the screenshot, and this is the source rectangle, and it draws this part of the screenshot into the specified rectangle. So we could just use it like this. We give it our screenshot, we give it our image view bounds where it's located, and then we just draw it onto a single pixel, like a single 1 pixel rectangle. And after that, we can just get the the color of the image by using this getPixel method, and it returns the color of the bitmap. So we could just use it like that. And after running this code now, it will look like this. So we kind of achieved what we wanted. We have a nice representation of the screenshot with all the sensitive data masked. We have nice lines there and the colors representing roughly what it looked like before masking. It's all good, right? It's working, but then we forgot about this guy. And the name for of it is Jetpack Compose. And of course, it's not going to work like that because Compose has a different view system. So the good thing is that Pixel Copy API still works for Compose because it's kind of view or framework agnostic, right? So it just copies pixels from one buffer to another. However, masking is kind of tricky. So there are no really classes because there are just composable functions. There is a lot of internal or private stuff that we actually have to access in order to like retrieve information that we need to mask. And Compose changes rapidly in a breaking way, oftentimes. So you cannot really rely that the method you use will be available like in a week or two. Yeah, so to help us visualize it, I kind of draw this tree. So we have, for example, this simple view tree, view group with some leaf nodes. The good thing here is we have actually the types here, right? Button, text, view, image view. However, for Compose, there is no types. It's just all layout nodes. You cannot retrieve information from there, like whether it's image or text, should I mask it or should I not? But the good thing is there is a second kind of parallel tree, which is called semantics tree. And this one contains all the info that we need, or almost all the info. We'll get to this later. For example, like for the container or for the view group, it has like is container true. For our button, it has the role button, text click, and same for image, for example. And this like semantics tree is basically the representation of accessibility services, accessibility tree on Android. So with these two trees, we could actually reliably mask Compose views. So let's just get back. We actually have to get back to our traversal method because in this case, we still have to check like whether the current node is, I mean, we're using some kind of reflection here, but we have to check the name of the class. If it's Android Compose view, then we know we have to now traverse the Compose subtree of the view, of the entire view tree. So we just created our like flavor called Compose view hierarchy node, and we don't need to like we also still have to return here early because the Compose view tree will be like traversed separately from the rest of the view tree. Yeah, so we go next to our Compose view hierarchy node, and we can use this. I mean, we have to cast here actually the view to this owner interface, and what this owner interface is basically, it's kind of connecting internal compose tree structure to the kind of binds the tree structure to UI part. So in this case, like if you have your Android compose view, it would implement this owner interface. And what's cool about this is the owner interface gives us access to the root node, which is exactly what we need, because from that point on, we can actually traverse the entire tree. What's not cool about this is that it's internal. So we have to do something in order to access this. And this something is actually adding this nifty annotation and saying, sorry, I don't care about your internal visibility. I just need this class and this method. I'm not sure how long it's going to work, because Compose can change this at one point, and then we are basically, yeah, I'm not going to say that word, but yeah, it's not good for us. But I assume they're not going to change this often, because this is like the very core part of the framework. So it would, if they change something, it would mean they kind of rework the entire framework, which is not going to happen probably. Yes, so now we can go further. The root node here exposes this children property, which we can just iterate over. And what we want to do next is actually retrieve the view bounds, right? The node bounds. Luckily for us, there is a bounds in window method, which is public, so we can actually just use it on the layout node, like this. What is unlucky though, the other two are internal again. So again, we're using like these two properties here. The first one is collapse semantics, and this basically returns us the semantics tree. Yeah, like I think it's a merge tree actually. So it's not like it doesn't return the root node, it returns the entire tree merged already into a single list, I think. And yeah, the other property is called is placed, and it indicates whether the node was placed into the component tree, and we kind of use this as an indicator that the node is visible or not. And yeah, now we have all the info that we need to mask or actually not mask, but identify whether this node is actually a text or an image. So we can check whether the semantics tree contains this property text or action set text. And this way we can reliably identify whether it's a label or a text input field, because those will certainly have this accessibility properties set. We can go further. What's cool about this semantics tree, it actually can also give us access to the text layout. So we can use this one to also, like, if there is a multi-line text, we can actually use this text layout to like nicely mask it per line. This method, unfortunately, might be heavy to execute on the main thread, but we still decided to do that and see how it goes in the wild. So if we get reports that it's super slow, I guess we'll just drop this entirely and then mask the entire text view because it's faster and easier. Yeah, a short note about this text layout. Because Compose returns us a special flavor of the text layout, which is like it contains some internal Compose stuff. We kind of created an abstraction over it called text layout and have different implementations for the old view system and for Compose. And the interface looks roughly like that. And yeah, it exposes all the things we need. Luckily, we could easily access them both from the Android layout and from Compose text layout. So it was just a simple thing to do. Yeah, with all that info, we can actually go and convert our like text node into our internal representation by wrapping the text layout result into Compose text layout. So if we are naive, we can go ahead and try to do the same thing for images, right? Just go and check whether the image has a content description, and now we know, okay, that's an image, so we can also mask it. But then out of curiosity, I went to GitHub and searched for this line, whether the content description is set to null, and it yielded 134,000 files, which means like almost nobody sets this content description to images, right? So we cannot really rely on that to know whether it's an image or not. which is unfortunate. And we had to look for other ways to do so. So we started looking into like how the images are being built in Compose and also in other frameworks. For example, Coil, if you use Coil for like loading images, it also has some certain elements that we looked at. And we noticed the pattern there. So this is, for example, from the Compose icon composable. It has this painter element, and that's a modifier. Then we also looked at the coil. It also has this modifier called content painter element. And there is another, I think this is from the old version of Compose, which is not yet anymore available. This is called painter modifier node element, which is also a modifier. All of those have like one thing in common, which is having painter in their name. So what we've done, pretty dumb actually, we went through the list of modifiers of a node and then check if the modifier has this painter in its name. And if it is, we know, okay, that's an image now, most likely, probably, I don't know. But like, assuming it will probably cover, I don't know, 80 to 90% of the cases, I think it was still worth doing that. Yeah, the only like thing you need to consider here is if your builds are obfuscated with R8 or ProGuard, whatever, you have to add ProGuard keep rules. But we've done this from the SDK side, and given that the rules are merged, we are kind of covered with that because like our customers who use the SDK, they will have this rule packaged with the app, so the names will not be minified or obfuscated. And yeah, like that, we can actually identify whether this is an image or not, and then convert it to our internal representation. And that's it, basically. We didn't have to do anything else for Compose because the rest of the code remains the same. It still runs over our like list of rectangles, over our internal structure, and then draws. And if you would execute this code on a Compose screen, it would be something like that. I forgot also to mention that we use Pocket Casts as a sample app because it's open source. It has both Compose and all the Android views, and they also using Sentry, I think, so it was pretty easy to kind of integrate this and use it. So shout out to them for open sourcing it. But yeah, this would be the result, and you can trust me, this is a Compose screen, I swear. Yeah, we still have some parts of our algorithm not covered, and the next one will be storing screenshots to disk. This is very simple, actually. There is only one caveat that we done is like we use the current timestamp as a screenshot name, so we can like recover this in case, I don't know, the app crashes. We know at which point in time this screenshot was taken. And yeah, we then just create this file, and then yeah, this is, you can find anywhere like in the docs, Stack Overflow, how to save bitmap into a file. And we use the JPEG format with the quality 80 here. Just a random number, honestly, didn't test it. Maybe we could use a even lesser quality here for better compression. We also still have to recycle the bitmap so it doesn't consume unnecessary resources, because at this point we don't need the bitmap anymore. Cool, we're almost through, I promise. So there is only one last remaining part, which is creating a video segment out of those screenshots that we saved. I'm not gonna cover how to really create a video because this topic can take another 2 or 3 talks probably, and it's very complicated. But I'll just run you through like high level how we do that. And you can also find a lot of samples on GitHub, for example, how to like encode video and decode it, like which parameters to use. But this is like a short overview. So we have to use like a media codec class from the Android SDK to encode screenshots into video frames. Then we also have to use this media maxer class to create like MP4 video out of those encoded frames. And last thing, I mean, if you know what you're doing, you don't have to do that, but I don't know. So I had to brute force the media codec settings to find like the most optimal ones for our case. So you can have a good balance between a good quality video, but still it's not like consuming megabytes of data. Yeah, here are some code examples. Basically, you would create a media codec like that. We use this AVC type because it's like the most popular one. It most likely will be available on any Android device. Then you would create this media format. You would have to pass the width and height of your screenshots there, so of our screen in this case. And then you would have to specify some properties here that kind of regulate how the images are encoded. Like bitrate, for example, regulates the quality of the video. The frame rate is like, we still have to maintain the frame rate at which we take screenshots, so we would pass 1 in our case here by default. And the iframe interval, it's an interesting one, so it kind of defines how often you should draw the full frame on the video. So for example, if you set this to 1, it means every second we would draw the complete screenshots into a video. However, if you set this to 5, for example, it would only draw it twice within 5 seconds. So like first one, and then would do only partial updates to the video. So like your quality will be a bit worse, but the video size would be smaller. So we like chose this, honestly, like, yeah, I think it's not a random number. I kind of brute forced it, but yeah, I think it works well for our case. So the video quality is still okay. There are some partial updates, like you still see some pixelated sometimes, like, yeah, pixelated frames, but it's not really that bad. And yeah, you would need, like in your encoder, you would have to start it. So you would call media codec configure. You would specify the flag encode because we want to encode frames into a video. Alternatively, you could specify decode if you are decoding. Then you would use the surface to encode the bitmaps onto, and you would just start. You would create a media maxer. You have to specify like the file name where your video file will be stored, and also the format in our case is MP4. And finally, your encode function would look like this. So you would just pass there a bitmap. You would use your surface to draw this bitmap onto. And finally, you would use the output buffer of the media codec to encode into like your MP4 video. I have no idea what's going on here, honestly. So, but yeah, it's like there are a lot of samples out there. You can look this up. Yeah. And last thing we have to do is actually use our video encoder. So we pass all the necessary parameters there. We check whether the time has passed, like 5 seconds since the last time we created the video segment. We start the encoder, iterate through our frames stored to disk, and then in the end we still have to release the encoder, so to release all the resources so it doesn't consume memory and CPU. There are some gotchas with video encoding. And the first one is adjust to block size. What this means is, I will explain it now, but basically what happened when we shipped the product, it basically started to randomly fail on some devices. And I was not sure what's going on until I saw this. This is taken from AOSP. And the important part here is that, video frames are conceptually divided into 16 by 16 pixel blocks, which means our resolution of the video has to be divisible by 16. And I didn't know that, and it was just randomly failing. So after discovering this, I went ahead to our code where we specify the screen size, and then we had to adjust to this block size, so it's always divisible by 16. Another gotcha was the Xiaomi devices. For some reason, they don't support hardware canvas. I don't know why. I just found this random answer on Stack Overflow. So we're just checking if it's a Xiaomi device, and then we use the software canvas instead of hardware. Otherwise, I don't think it was crashing, but it was encoding black frames, basically. So the video wasn't visible at all. Cool. We're almost through. As I mentioned, we only covered the first part here, but the other parts were not that hard to do. So we collected most of this telemetry already on our SDKs. So we just kind of packaged this together and sent. And as an end result, you would have something like this. You see our video with this screenshot example that we made. out there in Sentry dashboard. Okay, we don't have much time, but I still want to cover like quickly how we kept performance overhead low. First, we would downscale screenshots. So like originally we were taking screenshots at the full scale, kind of, so the full pixel size of the screen. Like for example, for Pixel 2, it would be like this 1440 pixels by 2880. But what we could actually do, we could scale this down a little bit, or not a little, but just scale. And in this case, we would have to take less pixels, like copy less pixels onto the bitmap, which is of course faster. So we just chose randomly here like the 1x, like the MTPI's density basically, and then we divide our real screen bounds by that number, and then this way it would be like something like 412 by 823, whatever. However, if you would run this, you would stumble something upon this, because the masking would still work on the on the real size of the screen, right? So you'd have to adjust that. Luckily, it's super easy to do. We just have to define this, calculate the scale factor x and y for width and height, and then before drawing the rectangles on the screenshot, you would have to pre-scale like the matrix and set it to the canvas. So there is a nifty method called pre-scale. You would just pass there the scale factors, and then it would correctly draw the rectangles after that, maintaining the scale size. Another thing, we want to only record changes on screen. So like if there's nothing changed on screen, it just stays static, you would not need to create another screenshot. So it's pretty easy to do. You would just add a onDraw listener to the viewTree observer, and then you would have some kind of Boolean, whether the content changed or not, which is set to true in case onDraw is called. And then in your capture method, you would check if the content didn't change, we actually don't have to take another screenshot because we already have that. Yeah. Cool. Yeah, this one. Yeah, speed up compose bounce retrieval. So I was randomly profiling our performance of the replay, and I stumbled upon this. I saw that the from view takes enormous amount of time. And when I dig deeper, I saw that this bounce in window takes, this is like one of the main parts that takes a lot of time. And this is executed for every node in the tree. So you can imagine that it's executed for many times on the main thread. When I looked into the implementation, I saw that what it does is actually traverses the view tree back from the leaf, back to the root, because it needs the root coordinates. I tried to visualize it quickly. We don't need to look at this, but basically, yeah, that's how it looks like. So for each node, it would traverse it back to get the root coordinates. And this does it for every node, every time. What's worse, it does it twice, because there is this bounce in root method, which calls again find root coordinates. So it does it 2 times. And this was a bug in Compose, which I just submitted a nice one-line fix, which was just approved pretty quickly. And yeah, was just overlooked probably at some point. There is another improvement. We could do that. We don't actually need to find the root of the tree because we already know the root, because we traversed from the root down, right? So we could actually just pass this root as a parameter there and use its coordinates for whatever is needed in this method. Yeah, that's what we've just done. We kind of copied this method over from the Compose code base to ours, and then has enhanced this with this logic, kind of past the root node. And yeah, the improvement was actually pretty significant. I think it saved like 35 to 40% of the main thread time, which is pretty nice. Cool. Yeah, and I'm through this overhead. A short note on the hybrid SDKs. We also have React Native Flutter SDKs, and we were curious, would it work for those or not? And surprise, surprise, it just works. Especially for React Native, because React Native just remaps the React views to native Android views, right? So it would just work for them. The masking would automatically work. With Flutter, it's a little bit more complicated because it has its own engine and view system. So we just expose some API to Flutter, and then they provide us with screenshots already masked. But the rest of the logic is executing on the Android SDK and iOS SDK. What's next? This feature is available beta to anyone for use for free for Android, iOS, React Native, and Flutter. We're going to release it stable early January. We want to have rage and dead clicks detection, which is a feature from our web replay product. It would basically indicate like if a user clicked many times within a short period on a button, we will report an issue that something might be wrong with your application. We want to also add a CPU and memory battery stats, so you could see like how it changes as your replay goes. And last thing, we want to kind of build a layout inspector in production because we capture the screenshot and we capture also the view hierarchy. We could send those both, and then we kind of overlay the view hierarchy over the screenshot, so you could have this nice experience as you are doing this in Android Studio, for example. This is just an example of our feature view hierarchy, but we only send it for crashes for now. But yeah, this is just an example of what it could look like. Here are some references to like documentation, GitHub repos. As I mentioned, our SDK is fully open source, so you can just go ahead and check the code that I try to show you. And with that, I'd like to thank you for coming. Yeah, and yeah, we don't have much time, so I consumed a lot of time. But if you have any questions, I'm available. Thank you.